Hey everyone, welcome back to the channel. If you're new here, don't forget to hit that subscribe button and ring the bell for more AI and machine learning content. Today, we're diving into something absolutely fascinating: information extraction and knowledge graphs. Now, you might be wondering, what exactly are these? And more importantly, why should you care? Well, here's the thing. Every single day, we interact with knowledge graphs without even realizing it. When you Google something and see that neat info box on the right, that's a knowledge graph. When Netflix recommends you the perfect show, knowledge graph. When Alexa understands the context of your question, you guessed it, knowledge graph. So buckle up, because by the end of this video, you'll understand how we can transform messy, unstructured text into beautiful, interconnected knowledge that machines can actually understand and use. All right, let's start with the basics. What exactly is information extraction, or IE for short? Information extraction is the process of automatically extracting structured information from unstructured or semi-structured text documents. Think of it as teaching computers to read between the lines, to understand not just words, but the relationships and meaning behind them. Let me give you a concrete example. Look at this sentence. Apple Inc. CEO Tim Cook announced the iPhone 15 in September 2023. To us humans, this is straightforward, but to a computer, it's just a string of characters. Information extraction helps the computer understand that Apple Inc. is an organization. Tim Cook is a person who is the CEO of Apple. iPhone 15 is a product, and all the relationships between these entities. Now, why does this matter? 3 words: scale, speed, and insight. First, did you know that around 90% of all data generated today is unstructured? We're talking about emails, social media posts, research papers, news articles. The list goes on. There's simply no way humans can manually process billions of documents. Second, automated information extraction works 24/7 and can process thousands of documents per second. Try doing that with a team of human analysts. And third, IE powers the modern AI applications we use every day: search engines that understand intent, chatbots that hold meaningful conversations, recommendation systems that seem to read your mind, and analytics platforms that turn text into actionable business intelligence. This is the foundation of turning data into knowledge and knowledge into power. So, how do we actually go from raw text to a fully functioning knowledge graph? Let me walk you through the pipeline. The journey has 5 major steps, and each one is crucial. Let's break them down. Step 1, text pre-processing. This is where we clean and prepare our text. We do things like tokenization, which is breaking text into words and sentences, part of speech tagging, identifying nouns, verbs, adjectives, and dependency parsing, understanding grammatical structure. Step 2, named entity recognition, or NER for short. This is where things get interesting. We identify and classify entities in the text: people, organizations, locations, dates, products, you name it. This is like giving the computer a highlighter to mark important information. Step 3, entity linking. Here we connect the entities we found to existing knowledge bases. For example, when we see Apple in text, we need to figure out, are we talking about the fruit or the tech company? Entity linking resolves this ambiguity. Step 4, relation extraction. Now comes the really cool part. We identify the relationships between entities. Tim Cook is not just a random person, he's the CEO of Apple. Einstein didn't just exist, he developed the theory of relativity. These relationships are the connections that make knowledge graphs so powerful. And finally, step 5, knowledge graph construction. We take all these entities and relationships and structure them into a graph format that can be queried, analyzed, and used by AI systems. Each of these steps can use different techniques, from rule-based approaches to deep learning models, and that's what we'll explore in the next sections. Before we dive into relationships, let me show you how named entity recognition actually works in code. Don't worry, it's surprisingly simple. Here I'm using spaCy, which is one of the most popular NLP libraries. Watch this. We import spaCy, load a pre-trained model, These models have been trained on millions of documents, and then we process our text. Google was founded by Larry Page and Sergey Brin in California. And just like that, the model identifies Google as an organization, Larry Page and Sergey Brin as persons, and California as a GPE, which stands for geopolitical entity, basically a location. This takes literally 5 lines of code. Amazing, right? Now let's talk about relationship extraction, the heart of building knowledge graphs. There are 2 main approaches. First, rule-based methods. These use pattern matching. Think of them as if this, then that rules. For example, if we see the pattern X is CEO of Y, we can extract that X has a CEO relationship with Y. Here's a simple regex pattern that does exactly that. We define a pattern, search for it in text like Satya Nadella is CEO of Microsoft, and boom, we've extracted the relationship. The second approach is machine learning, specifically deep learning models like BERT and GPT. These models are trained on massive data sets and can understand complex, nuanced relationships that rule-based systems would miss. Using the Transformers library, we can load a pre-trained relation extraction model, and it will automatically identify that Einstein developed the theory of relativity, extracting the developed relationship. Rule-based is great when you have well-defined patterns and need complete control. Machine learning is better for handling the messy, ambiguous nature of real-world text. In practice, the best systems use both, rules for high-precision extraction and ML for broader coverage. All right, now we get to the really exciting part. How do we actually build these knowledge graphs? Knowledge graphs are built on a beautifully simple concept called triples. Every piece of knowledge can be represented as a subject-predicate-object triple. Look at this. Einstein was born in Germany. We break this down into subject, Einstein, predicate, born in, object, Germany. When we connect multiple triples, we get a graph. Einstein was born in Germany, Einstein developed relativity, and relativity is a type of theory. See how these connections build a web of knowledge. Now, to actually build this, we use semantic frameworks. Let me introduce you to the big 3. RDF, Resource Description Framework. This is the W3C standard for representing information on the semantic web. It's like the lingua franca of knowledge graphs. Neo4j. This is a graph database that stores and queries knowledge graphs incredibly efficiently. It uses a query language called Cypher, which is super intuitive. SPRQL. Think of this as SQL for knowledge graphs. It's the query language for RDF data. Let me show you how to actually build a knowledge graph in code. We're using RDFlib, a Python library for working with RDF. First, we create a graph object and define our namespace. Think of this as our knowledge graph's address on the web. Then we add triples. Look how clean this is. Einstein is a type of scientist. Einstein was born in Germany. Einstein developed relativity. And relativity is a type of theory. We can save this to a file in turtle format, which is a human-readable format for RDF, and then we can query it. With just these few lines of code, we've created a queryable knowledge graph. How cool is that? Now, you might be thinking, this is all great, but where is this actually used in the real world? The answer? Everywhere. Let me show you. Search engines. Google's knowledge graph is probably the most famous example. When you search for Leonardo DiCaprio, you don't just get links, you get a knowledge panel with his age, movies, relationships, awards. That's all powered by a massive knowledge graph connecting billions of entities. Virtual assistants. When you ask Alexa, who directed Inception? She doesn't just keyword search. She queries a knowledge graph that knows Christopher Nolan is a director, Inception is a movie, and there's a directed by relationship between them. This enables contextual, intelligent conversations. Healthcare. This one's really exciting. Knowledge graphs connect drugs, diseases, genes, and symptoms. They're being used for drug discovery, finding existing drugs that might treat new diseases. They help doctors diagnose rare conditions by connecting symptoms. IBM Watson uses knowledge graphs to analyze medical literature and provide treatment recommendations. Finance. Banks use knowledge graphs for fraud detection, connecting transactions, people, accounts, and patterns. Investment firms use them for market intelligence, understanding how companies, industries, and economic indicators are connected. And here's a fun one: Netflix. Their recommendation engine uses a knowledge graph that connects you to actors you like, genres you watch, directors whose style you enjoy, and then finds shows that match multiple dimensions of your preferences. That's why their recommendations feel so spot on. The applications are truly limitless. Any domain that involves understanding relationships and connections can benefit from knowledge graphs. All right, let's see these knowledge graphs in action. I'll show you how to query them. First, let's look at a Sparkle query. Say we want to find all scientists and the theories they developed. Select asks for what we want to retrieve, the scientist and the theory. The where clause defines our pattern. We want things that are scientists who developed something that is a theory. And the results come back super clean. Einstein and relativity, Newton and gravity. It's like SQL, but for graph data. Now let's look at Cypher for Neo4j. This syntax is even more intuitive. Match looks for a pattern, a scientist node connected by a developed relationship to a theory node. Return gives us the names. But here's where it gets really cool. We can traverse the graph. This query finds all paths up to 3 hops away from Einstein. Want to know who Einstein collaborated with, who studied under him, what influenced his work? This query will show you the entire web of connections. This is the power of graph queries. You can explore relationships and discover insights that would be nearly impossible to find in traditional databases. Now, I wouldn't be doing my job if I didn't talk about the challenges and where this technology is headed. Let's be real. Building accurate knowledge graphs is hard. Here are the main challenges. Ambiguity. Apple could be a fruit, a company, or a record label. Natural language is inherently ambiguous. Domain-specific terminology. Medical texts, legal documents, and technical papers use specialized vocabulary that general models struggle with. Scalability. Google's knowledge graph has over 500 billion facts. Storing, updating, and querying graphs at this scale requires serious engineering. Consistency. How do you keep information up to date when your sources conflict? What happens when Tim Cook retires and Apple gets a new CEO? Multilingual extraction. Building knowledge graphs that work across languages is incredibly challenging. But here's the exciting part. The future is incredibly bright. Large language models like GPT-4 and Claude are revolutionizing information extraction. They can do zero-shot extraction, meaning they can extract information without being specifically trained on that task. Game changer. Multimodal knowledge graphs. The future isn't just text. We're building knowledge graphs that integrate images, videos, audio. Imagine a knowledge graph that knows not just that Mona Lisa is a painting, but actually understands the visual features of the painting itself. Automated graph construction. We're moving towards systems that can automatically build and maintain knowledge graphs with minimal human intervention. Federated learning. Building knowledge graphs while preserving privacy. Different organizations can contribute to a shared graph without exposing their raw data. Explainable AI. As knowledge graphs power more critical decisions, we need them to explain their reasoning. Why did this system make this recommendation? What facts and relationships led to this conclusion? We're at the beginning of a knowledge revolution, and it's an incredible time to be learning about this technology. And that's a wrap. Let's quickly recap what we've learned today. First, Information extraction is the bridge between unstructured text and structured knowledge. It's how we teach machines to read and understand. Second, knowledge graphs represent knowledge as interconnected entities and relationships, making information queryable and machine understandable. Third, this technology is already powering the AI applications we use every day, from Google Search to Netflix recommendations to medical diagnosis systems. And finally, with large language models and multimodal AI, the future of knowledge graphs is even more exciting than the present. I hope this video gave you a solid understanding of information extraction and knowledge graphs. If you found it helpful, please give it a thumbs up. It really helps the channel grow. Don't forget to subscribe and hit that notification bell so you don't miss our next video. Thanks so much for watching, and I'll see you in the next one. Keep learning, keep building, and keep being awesome.